Ever stop to think that the way a star spins, that it could actually link back to these tiny, tiny jitters in the early universe?
Yeah, quantum fluctuations, basically, setting these huge balls of fire spinning. It's pretty wild.
It really is.
Yeah.
Welcome to the deep dive. We try and take these, huge cosmic ideas and make them make sense.
That's the plan. And stellar rotation, it's not just some random detail, it's fundamental. It shapes, well, everything about a star's life.
How it's born, how it evolves, right?
Exactly. How it behaves, its magnetic fields, its lifespan. It's all tied in.
And look, space is vast. It can feel like too much sometimes.
Definitely overwhelming.
But today, we're zeroing in. We've got a mission. How do stars spin? How do scientists figure that out from so far away? And crucially, what does it tell us?
And we've got some amazing data to work with now, especially from the Gaia mission. It's been a real game changer.
You mentioned Gaia. How does it compare to what we had before? I remember hearing about older studies.
Oh, absolutely. Think back just maybe 20 years or so. There was a big compilation, the Glabaki study. It had around 11,000 stars, which was great then.
11,000.
But now, Gaia, we're talking millions. And missions like Kepler, they gave us incredibly detailed views of smaller patches of sky.
Right. Kepler was amazing for finding planets, and it measured star brightness so precisely.
It was fantastic for rotation periods from starspots, too. But Gaia is surveying the entire sky. The scale is just different.
Okay, so that's our focus for this deep dive.
Yeah.
How do we know how fast these things are spinning? And why should we care? Let's jump in. Why spin at all? Where does it start?
Well, it starts way back. Before the star even is a star, you have these enormous clouds of gas and dust.
The stellar mysteries.
Exactly. And they aren't perfectly still. There's always some slight residual motion, some angular momentum.
Like a tiny bit of swirl.
Kind of, yeah. And as gravity pulls that cloud together, making it smaller and denser.
It spins faster, like the ice skater pulling our arms in.
Precisely that. Conservation of angular momentum. And the really mind-blowing part is that initial tiny swirl. Its origins might genuinely trace back to those quantum fluctuations in the very, very early universe.
Wow, tiny density variations getting amplified over billions of years.
Leading to the rotation of galaxies and eventually the stars within them. It's all connected.
Okay, still wrapping my head around that. But they aren't solid balls spinning uniformly, are they? I think I read the sun spins differently.
That's right, they're fluid, giant balls of plasma. So they experience what we call differential rotation.
Meaning different parts spin at different speeds.
Exactly. Our sun's a perfect example. At its equator, it takes about 25 days to go around once.
Okay.
But near its poles, it's much slower, closer to 34 days.
Why the difference?
It's complex, tied to how energy moves inside the star, convection currents, magnetic fields. But the key thing is, it's not rigid. And this rotation, especially the speed at the equator, exerts an outward force. A centrifugal force.
Like being on a fast merry-go-round.
Kind of. And it makes the star bulge out slightly at the equator and get a little flattened at the poles.
So they're not perfect spheres.
Nope. For the sun, this ablateness is tiny, like 8 parts per million difference between the equatorial and polar diameters. Almost negligible.
Almost.
But for stars that spin really, really fast, this bulge can be significant. You can get quite noticeably squashed stars.
Okay, so a squishy, differentially rotating plasma ball. Got it. And the spin isn't just a curiosity. It actually does things, right? Affects the star.
Oh, hugely. It's fundamental. For one thing, rotation, especially that differential rotation, is thought to be crucial for generating the star's magnetic field.
The stellar dynamo.
Exactly. The churning, rotating plasma acts like an electrical generator, and then that magnetic field plays another role. It interacts with the stellar wind.
The stream of particles flowing out from the star.
Right. The magnetic field kind of catches that wind, and as the wind flows outwards, carrying mass and momentum away, it effectively drags on the star's rotation. We call it magnetic braking.
Ah, so the star is constantly putting the brakes on itself.
In a way, yes. It means stars tend to be born spinning relatively quickly, and then they gradually slow down over their main sequence lifetime.
That's a cool picture. Born fast, slow down with age. What else? Does spin affect the inside of the star?
It does. Rotation can drive mixing processes within the star, stirring up the layers and bringing different chemical elements from the core towards the surface, or vice versa.
And that would affect how it burns its fuel.
Potentially, yes. It can impact its evolution, how long it lives, maybe even what elements it produces. And there's another really neat consequence of that slowing down.
Go on.
Because stars seem to slow down in a reasonably predictable way as they age. If you can measure how fast a star is spinning now.
You can estimate how old it is.
Bingo. That's the basis of gyrochronology, using the star's spin rate as a kind of cosmic clock.
Wow. Okay, so spin connects to magnetic fields, stellar wind, internal mixing, and age. It's way more important than I thought.
It really is central to understanding stars.
Which brings us back to the big question. How? How do we actually measure the spin of something that's light years away? Seems impossible.
It does seem impossible, but astronomers have got some very clever tricks up their sleeves. There are two main methods.
Okay, method one.
Method one uses spectroscopy, looking at the star's light spread out into a spectrum, like a rainbow.
And looking for specific lines in that spectrum, absorption lines.
Exactly. Those dark lines tell us about the chemical elements in the star's atmosphere. Now imagine the star spinning. One side is rotating towards us, the other side away from us.
Right, like one edge is blue shifted, the other red shifted, the Doppler effect?
Precisely. So the light from the approaching side is slightly compressed, shorter wavelength, bluer. The light from the receding side is stretched, longer wavelength, redder.
Okay.
And when you look at the combined light from the whole star disk, what happens to those sharp absorption lines? They get smeared out, broadened.
Ah, because you're seeing light shifted both ways at once.
Exactly. The faster the star rotates, the bigger the Doppler shifts at the edges, and the broader those spectral lines become by measuring that broadening.
You can calculate the rotation speed?
Well, the projected rotation speed, what we see along our line of sight, we call it V sin I.
Okay, V sin I. That's clever. Using the smearing of light. What's method two?
Method two is photometric. It's about watching the star's brightness change over time, very subtly, usually.
How does rotation change brightness?
Many stars aren't perfectly uniform spheres of light. They have features on their surface, starspots, for instance.
Like sunspots on our sun. Cooler, darker patches.
Exactly. Or sometimes brighter patches called faculae. As the star rotates, these features are carried across the star's visible disk.
So if a big spot rotates into view, the star looks slightly dimmer?
Correct. And then maybe it rotates out of view and the star brightens up again. Or a bright patch rotates into view.
So the star's brightness flickers, almost, on a regular cycle.
If the spots last long enough, yes. You get these small, often periodic variations in brightness. By timing how long it takes for that pattern of brightness changes to repeat.
You get the rotation period. How long it takes to spin once.
Exactly. That's photometric modulation.
Okay, so spectroscopy gives speed from line broadening. Photometry gives period from spots moving across. Cool. Now, you mentioned earlier studies like Globocki.
Yeah.
What was the picture like before Kepler and Gaia really hit their stride?
It was patchier. That Globocki compilation, around 11,000 stars, was invaluable, but it was mostly brighter stars, nearby stars, some clusters, primarily based on that spectroscopic line broadening method.
So we had some idea, but maybe not the full range.
Right, and measuring those tiny brightness variations for the photometric method was really challenging from the ground for lots of stars.
Then along came Kepler. That changed things.
Oh, dramatically.
Yeah.
Kepler stared at one patch of sky for years, measuring brightness with incredible precision. It was designed for planet hunting, finding those tiny dips when a planet crosses a star.
Transits, yeah.
But that same precision was perfect for seeing the much smaller variations caused by starspots rotating.
Ah, so it could measure rotation periods for way more stars.
Thousands upon thousands. The main Kepler mission gave us something like 34,000 reliable rotation periods. Its follow-up mission, K2, added maybe another 30,000.
Wow. There must have been a flood of data. What did we learn from that?
So much. It revolutionized our understanding of star spots, how long they last, how they're distributed. It massively improved gyrochronology, letting us calibrate that age-spin relationship much better.
Okay.
We learned more about how magnetic braking really works, how it depends on stellar type. It even helped with astroseismology, studying starquakes because rotation affects those vibrations. And of course, understanding the host stars of the planets Kepler found.
So Kepler gave us this incredibly detailed, high-cadence look at rotation for a big sample. But now, Gaia, you said it's like watching the whole movie.
Yeah, Gaia's approach is different, but equally, if not more, revolutionary in scale. It's using both methods, photometry and spectroscopy, but across the entire sky.
Okay, let's break that down. How does Gaia do the photometric rotation measurements? You said its measurements aren't as frequent as Kepler's.
That's true. Gaia scans the sky repeatedly, so it doesn't stare constantly like Kepler. Each star gets observed maybe 70, 100 times over the mission lifetime, spread out Not ideal for very short periods, maybe,
For sure.
but it's observing billions of stars all over the sky, not just one patch. And it measures brightness in 3 different color bands, G, BP, and RP.
Does having different colors help?
It does. It gives you information about the temperature, the features causing the variation. Are they cool spots or hot faculae? And Gaia goes much fainter than Kepler, down to magnitude 21 or so. It sees many more stars, especially dimmer, redder ones.
So sheer numbers, all sky coverage, color information, and faintness reach.
Exactly. Even with less frequent sampling per star, the overall data set is immense.
And have we seen results from this Gaia photometry yet?
Absolutely. Even with the earlier data released too, a study by Lanzafame and colleagues looked at about 500,000 stars Gaia flagged as variable. They managed to pull out nearly 150,000 rotation periods, attributing them mostly to starspots and faculae, what astronomers call BY Draconis variables.
150,000 periods from DR2 alone. What kinds of stars were they?
A mix: regular dwarf stars like the Sun, some slightly more evolved subgiants, even very young, active T-Tauri stars. Plotting their properties, like brightness versus color, revealed patterns related to how spin evolves and how those magnetic dynamos work.
And the more recent data release 3. More progress there.
Definitely. Another study, Di Stefano et al., focused specifically on stars showing variability similar to our Sun's magnetic activity cycles. They started with almost 500,000 candidates, most newly identified by Gaia as variable.
And found periods for how many?
They pinned down about 150,000 well-defined rotation periods from that sample.
Another 150,000.
Yeah, and importantly, their analysis was sensitive enough to pick up a lot of really fast rotator stars spinning in less than a day.
Less than a day. That's incredibly quick for a star.
It is. These were often missed by previous surveys because you need fairly frequent observations to catch such rapid changes. Gaia's multiple observations, even if spaced out, allowed them to find these.
Do they show examples?
They do. They showed the light curve, the brightness measurements over time. For one specific star, Gaia DR3 6503897945888972544, demonstrating how they extract the period even when the pattern isn't perfectly repeating, because spots evolve.
Okay, so Gaia's photometry is yielding huge numbers of rotation periods across the whole sky. What about the other method? The spectroscopy.
Right. Gaia also has a spectrograph, the radial velocity spectrometer, or RVS.
I thought that just measured how fast stars are moving toward or away from us.
That's its primary job, yes. And Gaia DR3 released radial velocities for, wait for it, 33 million stars.
33 million.
Yep. Stars with temperatures between about 3,100 and 14,500 Kelvin. But the RVS spectra contain more information than just the Doppler shift of the whole star.
Line broadening again.
Exactly. The processing pipeline for the RVS data carefully analyzes the shape of the spectral lines. After accounting for broadening caused by the instrument itself and things like turbulence in the star's atmosphere.
There's still some broadening left over.
Often, yes. And they quantify this extra broadening, calling it V-broad. The assumption is that the dominant cause of this V-broad is the star's rotation.
So Gaia is measuring V sin I, the projected rotational velocity, from its spectra.
That's the idea. A paper by Fremont and colleagues described how this was done for DR3.
And how many stars have this V-broad measurement?
The Gaia DR3 catalog contains rotational broadening measurements for over 3.5 million stars.
3.5 million.
It's staggering. By far the largest sample of spectroscopic rotation indicators ever compiled, covering all sorts of stars across the Hertzsprung-Russell diagram, the map of stellar types.
How confident are we in those measurements?
They did extensive comparisons with other big spectroscopic surveys, Gaia, Apogee, Lamos, that also measure rotation, and found generally good agreement, which is very reassuring.
Okay, so Gaia gives us photometric periods for hundreds of thousands and spectroscopic broadening for millions. That's just transformative.
It really is. It moves us from studying individual stars or small groups to analyzing the rotational properties of entire stellar populations.
With all this data, we must be seeing the extremes now. You mentioned fast rotators.
Oh, yeah. Take Regulus, a bright star in Leo. Its projected rotation speed is about 317 kilometers per second.
Whoa! How fast is that in terms of period?
It spins once every 15.9 hours, and that's incredibly fast. It's estimated to be spinning at about 86% of its critical breakup velocity.
Meaning if it spun much faster, it would literally fly apart.
Pretty much, yeah. And it's significantly flattened. That ablateness we talked about is quite large for Regulus, maybe around 0.32. Vega and Achernar are other famous rapid rotators.
Spinning themselves nearly into oblivion. What about the other end? Super slow spinners.
There are those too. Kepler found a fascinating one called KIC 11145123, its rotation period. About 100 days.
100 days, compared to 16 hours for Regulus or 25 days for our sun's equator.
Exactly. It's incredibly slow. And because it spins so slowly, it's almost perfectly spherical. Measurements suggest the difference between its equatorial and polar radius is only about 3 kilometers. It's been called the roundest natural object measured.
From 86% of breakup speed to almost perfectly round, the diversity is amazing.
It really showcases the vast range of possibilities out there.
And I guess having all the other information, Gaia provides precise distances, motions, brightnesses, colors, helps interpret these rotation measurements.
Absolutely essential. For example, understanding the strange bimodal or two-peaked distribution of rotation periods seen in cool M-dwarf stars requires knowing their accurate distances and temperatures, which Gaia provides.
Right.
Or studying stars in open clusters. Gaia lets us identify cluster members with high certainty and know their ages precisely, so we can then use the rotation data, both periods and V-Sini, to track exactly how spin evolves with age and stellar mass in exquisite detail.
It connects everything together.
Exactly. The astrometry, the photometry, the spectroscopy, they all reinforce each other.
Okay, wow. So let's try and wrap this up. Gaia is just pouring out data on stellar rotation, using both the flickering from star spots to get periods and the smearing of spectral lines to get speeds.
And the scale is unprecedented. Hundreds of thousands of periods, millions of broadening measurements.
We've gone from that early 11,000 star sample to this immense data set, revealing the full spectrum from stars spinning incredibly fast, almost tearing themselves apart, to these super slow, almost perfectly round ones.
It allows us to study trends across huge populations, not just individual examples.
Giving us much deeper insights into those fundamental processes: magnetic fields, stellar winds, internal mixing, and nailing down that gyrochronology, the age-spin connection.
It's a phenomenal resource for understanding stellar physics.
It really feels like we've turned a corner.
Yeah.
And, with this incredible census of how stars spin, it makes you wonder, what's next? What unexpected links might pop up? Like, could a star's spin somehow influence the kinds of planets it forms? Or how habitable they might be?
That's a fantastic question. People are definitely looking into star-planet connections, and rotation is surely part of that puzzle.
Or even bigger scales. Could the collective spin of stars in a galaxy somehow affect the galaxy's evolution over cosmic time in ways we haven't thought of?
It's possible. These huge data sets often reveal subtle correlations or entirely new phenomena once people start digging into them in creative ways. The discovery potential is still enormous.
It feels like we've just been handed this incredibly detailed map, and now the real exploration begins.
That's a great way to put it. The data is there, and the science community is hard at work deciphering all its secrets. It's a really exciting time in stellar astrophysics.